share my screen. So you can station, right? Okay. So as you know, in the last class we were discussing, or in the last few classes we have been discussing about electrostatics and how to calculate electric field, how to use Gauss's law, or how to make use of the symmetry that is present in our system in order to calculate fields and potentials. Then we also spoke about multipole expansions and like how one can express the fields or potentials for a dipole, electric dipole, and things like that, right? So today what we'll do is we'll mostly concentrate on magnetostatics. Okay, and we would see how, just like we had Gauss's law for electrostatics, how we have Ampere's law here. And so it also makes use of the symmetry that is present in the system. You would see that a current carrying wire results in some magnetic field around it. And then if you have some some charges around it, that they would experience certain forces if they are moving. So we would talk about magnetic forces, and we would also discuss about how to calculate, like how to make use of free currents that we provide, and make use of that in order to find the total field, and how magnetization comes into picture and things like that. Okay, so we would discuss about the basic concepts and some problems we would like to solve, and then if you have some doubts we'll try to address them. Okay, so now let's start with magnetic forces. So we know that suppose if you have a current carrying wire, okay, like this, then that, so basically, what is current? It's like charges in motion, right? So just like static charges result in electric field, when you have charges in motion, they result in a magnetic field. And so if you have a current carrying wire like this, you would get magnetic fields in like circling it like this, right? So these are the field lines. So it's like the right hand thumb rule, which tells you about how the magnetic field is around a certain current carrying wire or some current distribution. Okay. But now another thing that was observed is that suppose if you have two wires, okay, and this has some current I, this has some same current or different current, this is another current I. And what happens is this experience some force, okay, towards this wire. So this in a way tells us that when you have charges in motion in a magnetic field, they experience certain kind of force. Okay. So this brings in us to the fact that there are some magnetic forces. So just like if you have some charge in an electric field, it would experience a force Q into E. Similarly, if you have some charge Q, which is moving with some velocity V in a magnetic field, then it would experience a force which is given as Q into V cross B, right? So the total force, so if you have both electric and magnetic field, the total force will be given by QE plus Q into V cross B. It's important to note that because the magnetic force is always perpendicular to the direction of motion of the charge, it does no work. Okay, so magnetic forces do no work. Now, this is for a single charge. Now, if you have a charge distribution, so suppose if you have a current carrying wire where you say that, so the distribution is such that you have lambda charges over dl length, and that is moving with velocity v. Then what would happen? You would extrapolate the same concept to an integration, right? Where you have v cross b into lambda dl over that like the length segment of lines over the length of the line segment. Sorry, so over the length of the segment of the current carrying wire. So if you do that, then what you can say here is that, see, lambda into V is actually the current that is flowing per unit time through that wire. So this gives you the expression for magnetic force that a segment of current carrying wire feels when kept in presence of some field B, right? So similarly, now what can happen is, so this is what I was talking about, a current carrying wire. But now if you have some distribution like this, where you have a surface current density which is flowing over a sheet, okay, so there you can define the surface current density as sigma into V, where sigma is the surface charge density and V is the velocity of the charges. And this can also be defined as the, so dl perpendicular. So it's like, so dl perpendicular is the width, as you can see, along the direction which is perpendicular to the flow of the current, right? So now, again, if you write the expression where you write, now you are writing I, or the current, as sigma into V into dA, right? So if you do that, you would get a similar kind of integration, right? And one can also extrapolate it to 3 dimensions. And in that case, you have volume current density, which is given by rho into V. And this is how it looks like. Okay. So this tells you that if you have some charge distribution where the charges are moving, and if there is a presence of a field around in that place, then it would experience some force, which is given by this expressions here. Okay. So now if you have some current I which flows down a wire of some radius A, okay, and here it's if it is uniformly distributed over the surface, what would be the surface current density? So there we would use this relation, right? So what it is now telling you is that you have current I flowing over a wire, okay? So if you have some wire where current is flowing through the wire in a circular fashion, so the surface current density is given as di by dl perpendicular, right? Where dl perpendicular actually is the circumference of the circle. So if you do that, you get k something like this. K is given as I by 2 pi a, right? Because length perpendicular to the flow is the circumference. The second part of the question says that now suppose this current is distributed in such a way that the volume current density is inversely proportional to the distance from the axis. What is J? J is the volume current density, right? So it says that J is proportional to inversely proportional to S, like J is equal to alpha by S, where S is your radial distance from the axis, okay? And you know that the total current is given as J into dA. So if you do that, this is just how you are using the, so it's a basically a wire. So you're using the cylindrical coordinate system, and this is how the surface, the perpendicular area would look like. And if you, this is the segment area element of the cylinder. And then if you do that, this is just calculations which give you that this is how the volume current density will look like. So this in a way tells you that if you have some distribution, depending on which coordinate system you are, or which how your structure is, you have to use this concepts to express how the current gets distributed over a surface or over a volume. And now if you know that, and if you know, suppose the field around it, you can find the force that it would experience, right? So, and this is how the force expressions would look like in 1D, 2D, or 3D. Okay. So now that we know the basics, let's see what is the force of attraction between two long parallel current carrying wires. Okay. So can any of you tell me that suppose if you have two long parallel current carrying wires, parallel meaning the currents are flowing in the same direction. Okay. So what kind of force will one current exert on the other? Is it an attractive force or a repulsive force? Any idea? Okay. So let's see. Okay, repulsive. Okay, someone says repulsive. So if you have currents flowing in the same direction, you say that it's repulsive. Why do you think so? Like, what's the thought process here that you are using? Okay, so let's see what basically happens, right? So if you have currents flowing in different directions, they would experience a repulsive force. While if the currents are flowing in the same direction, they experience attractive force, right? It's quite uh, so unexpected if we just think of analogy from uh, like charges repel and things like that. But it's not that concept that we'll be using here. We'll see how to calculate the force. So basically, we already know that if you have some charges that are flowing and if there is a magnetic field present there, they would experience some force, right? And that is given by the formulas that we just discussed, something like this. So it's perpendicular to the direction in which the charges are flowing, and it's also perpendicular to the magnetic field that is present there, right? So now what you can see here is that you have these two charges, right? I1 and I2, and the distance between, so the two wires, current carrying wires, and the distance between them is given as d, right? So now this is the force expression, right? F is equal to I into dl cross b. Now here, if you suppose this is your current carrying wire, what is the field that one would experience at this point, right? We already know that. We know the field for a infinitely long current carrying wire, right? And that is given as mu 0 I by 2 pi d. This is something we derived in the last class from the Biot-Savart's law, right? So now that we know what the field is, and we also know that the charges in this wire is flowing in this direction. So we can use this relation to find the force that this, like this wire would experience because of the field coming from this wire, right? So if you do that, this is what you get, right? So now here there's an integration over the entire length of your of the second wire. And if it is an infinitely long wire, you can see that the force becomes infinity. But what's interesting is that the force per unit length, obviously in nature, we don't have infinite wires. So the force per unit length, if you find, it would be given as mu 0 by 2 pi I1 I2 by d, right? And so if you think of the right hand thumb rule, and this is the expression, so you would see that the forces are directed towards this, towards the first wire. So it's an attractive force, right? If the field direction was opposite, you would have minus here, and that would signify that it's a repulsive force. Okay. So now, thinking along similar lines, if you have two infinite straight line charges. Okay, so before I proceed, it's clear, right, why it's an attractive force? Okay, so I'll consider that it's clear. Okay, so now that you have, so in this case, you have two infinite straight line charges, lambda, okay, and they are at a distance d apart, moving at some constant speed v. Okay, so basically, this is a line along which lambda charge per unit length is moving at a velocity v. And another wire is this, which is at a distance d. So what is the effective current that is flowing through this wire? Can you or this straight line? Can you tell me? Any idea? Like, because we just discussed that if you have some wire where you have some charge distribution and if they are moving, basically what is current? Current is charge flowing per unit time, right? So from this two values that are provided here, can you say what is the effective current that is flowing over this straight line? And what is the current that is flowing over this straight line? Something like that. Okay, so it should be lambda into V, right? Just as we discussed previously. So here, as 1 second, I'll go back to, so something like this. So lambda is the charge per unit length. It's moving with velocity V. So the charge that flows per unit time is given as lambda V into dt. And then so the current is given as lambda into V, right? So basically, in this question now, it boils down to the fact that you have two wires where the effective current in each wire is given as lambda into V, right? And it's now said that how great would V have to be in order for the magnetic attraction to balance the electrical repulsion? And it's important to solve this question because this would tell us something. So now that we know that basically we have two current carrying wires, we know what is the force that one wire would experience because of the other, right? And that is given as mu 0 by 2 pi I1, I2. There was a product of I1, I2. And now if you replace it by lambda into V, this is what you get, right? Lambda square V square by D. Now, we also know that because of this line charge, like a line of charges, what is the electric field of one wire? And this is what we get, right? This is what we already know from electrostatics. And now, what is the force per unit length that suppose this wire would experience because of the electric field produced by this? So we can just multiply by the charge per unit length, right? Because electric force is given as Q into E. So if you do that, this is your electric force. So if they have to balance, you can see that the velocity has to be equal to the speed of light. So this in a way tells you that the electric forces always dominates, and in order to balance the electric repulsion, the speed of the charges has to be equal to the speed of light, which is so you are never having the wires moving that fast, and so the electric forces always dominate. Okay. So that was about magnetic forces. Now we move to divergence and curl of B. Okay. So if you have suppose this dot shows a infinite straight wire with a which is flowing out of the page. Okay. So the current is coming out of the page, and we know that this is how the field lines look around it, right, from Biot-Savart's law. So now, if we want to find the integral of B around some circular path of radius S, okay, centered at the wire, how do you do that? So you have some circular path and you're doing an integration. It's a line integral. So it's mu 0 I by 2 pi S into dl, right? And if you do an integration over the entire length of the over the circumference, you get 2 pi S. So basically it's given as mu 0 I. So as you can see, it's independent of S, right? And now you can say that, do we actually always have to have a circle, or can it be any loop? So as you can see here, that if you take into consideration the vector notation of magnetic fields, and then if you take a small element, okay, line element, that would be given as SD phi, right, along the arc. And then if you do an integration, you get the same value. So basically, whatever the loop is, if it encircles or if it encloses this current carrying wire with current I, then the line integral is given as mu naught I, right? And then if you use Stokes' law, you see that you can write the curl of B as mu naught J, right? J is the volume current density of this wire. So basically, this is called the Ampere's law, right? So it's just like we had Gauss's law for electrostatics. Now you have Ampere's law for magnetostatics. And you can see that whenever there is some kind of a symmetry, or it makes it easier for us to calculate the fields by using the Ampere's law, as you can see here. So we already know this expression, but just by the Amperian loop, you can also get back to the same expression, and it's much easier to solve. Okay. And so this is the integral form, and this is the differential form of Ampere's law. Okay. Now that we know this, we want to find the magnetic field of an infinite uniform surface current K. Okay. So it tells us that this is some sheet of current where the surface current density is given as K. Okay. And this is how the direction is along X. Okay. Now you want to find the magnetic field for this, right? So this is important because this would in a way tell us a lot about numerous questions that can come in our way. I'll show you how. So what do? We consider an Amperian loop. So it's analogous to when we discussed about a surface charge density, and we saw what is the field for the surface charge density, right? And we saw that it's independent of the distance from the sheet. And then we also calculated what we should get if you have two charge density, such sheets with surface charge equal and opposite to each other, right? and we calculated the field inside and outside, and we saw that outside the field is 0. So that was what we did for electrostatics. We are doing a similar analogous problem now for magnetostatics. Okay. So we consider this Amperian law, right? So if you consider this, what do you get? B dot dl. So 2 into B into L, where length, this is the length of your Amperian loop. And what is the charge that it encloses? It encloses mu naught K into L, right? Because yes. Any question? Okay. So we know the definition of K, right? K is the unit. Okay. If you have a question, you can ask me. Otherwise, can you mute yourself? Okay. So we know that. Okay. NS. Okay. Can you please mute yourself? Okay. You are unable to see the video. I guess. Can you just log out and log in again? I guess it's a problem for your end because others can see, right? Can't see the chat. Okay. Okay, just try logging out and logging in again. Yeah. Okay. So now if you do the okay. So what is the current that is enclosed in this region? So we know that K is given as dI/dL perpendicular, right? So what is the total current in this region? It's given as K into L. This is the perpendicular length. So now if you do that, you can actually find the field, right? Can you see the slides now? Okay, so I'll consider. Oh no. Okay. Can others see? Because I can see in my other device here. Okay. So NS, I think there's some issue with the network at your end because I have logged in through another device and I can see my slides. So I think it's not a problem from this end. Okay. Right. So what would happen? You can see from here that you can find the field, right? And now if you use the same right-hand rule, that would also give you these directions, right? And you can see that if you have a current which is flowing in this direction, below the sheet, it would flow in the positive y direction, while above the sheet, it would flow in the minus y direction, right? And as you can see that the field is independent of the distance from the plane, right? Just like the electric field of a uniform charge, a surface charge. Okay. So now suppose if you have now like this is something to remember, right? Something very fundamental, and you'll see how useful this understanding is. But let's now move on to the magnetic field for a long solenoid. Solenoids are widely used for as electromagnets, and it has wide usage. So let us see how the magnetic field is for a long solenoid. Long meaning that you have it's infinite in length, okay? And it has n closely wound turns per unit length, and the radius is r, and it's carrying some steady current I, right? So here, if this is how your solenoid looks, you can think of this as something with a surface charge density given by K, which is along the azimuthal angle, right? Along which flows along the surface, the curvilinear or the curved surface of your cylinder. So now, if this is a structure, how should the field be? Okay, should it have a radial component? So if you just think of this fact that suppose you have this current here, okay, and in case if it had a radial component, then by reversing the, but just by turning the coil upside down, the field direction should change. But from symmetry point of view, it should not alter the radial field. So this in a way tells you that for a structure like this, there should not be a radial component of the field. Okay. Now, should it have a circumferential component, like B phi, which changes along the azimuthal angle? So even that is 0. Why? Because what you can do is you can consider a Amperian loop, right? A circular loop, which is concentric with the solenoid. And you would see that it encloses no field, right? And there, just by the Ampere's law, it tells you that because the enclosed current is 0, your B phi should be 0, right? So this tells you that the magnetic field for an infinite closely wound solenoid should run to its, it should run parallel to its axis, along its axis, right? And from the right hand rule, you can think of how it should be. So it should point upward inside the solenoid and downward outside for this structure, right? Okay. And if you change the field direction, it should get reversed. So now we want to find how the field should be, right? So what you do is you consider two Amperian loop, okay? One is this, another is this. So let us see for the first Amperian loop first. So here, what happens? You know that the field is along the axis, right? So if you apply the Amperian loop, you would see that there will be some field at A distance, right? And some at B. So if you use just the integral, you would get something like this. But as you can see, this loop encloses no current, right? So this tells you that the field outside does not depend on the distance from the axis and they are equal, right? But we also know that very far from the solenoid, the field should go to 0. So this in a way tells you that this BA equal to BB should be equal to 0 when this A and B, when these points are outside the solenoid. Now what happens for this loop? Here, again, if you use the same Ampere's law, you would see that obviously here along this line, the field is 0, but there is some field B along this line, right? So you can write B into L is equal to mu 0 I enclosed. And now you have an enclosed current, which is given as N into I into L, right? N is the number of turns per unit length. So now if that is the case, what you get this is the magnetic field. So for an infinitely long solenoid, you see that all the field lies within the solenoid, while outside it's 0, right? And the field is uniform. So this is how the solenoid is analogous to a parallel plate capacitor in electrostatics, okay? But in nature, we do have some field outside, some fringing effect, which happens because our solenoids cannot be actually infinite in length. Okay. So now, if you know how the field is, can you calculate the self-inductance of a solenoid? Now, what is self-inductance? So whenever you have some field lines, okay, so you have a solenoid, there's a field inside, so there'll be some field lines coming in, right? So there'll be a flux that would be associated with the solenoid. So what is the flux? Through one turn, flux is given as, so the field intensity into the area, right? Area facing the magnetic field lines. So area perpendicular to the field lines. And that is given as, suppose this is A, so it's given as mu 0 Ni into A. And you can have, so for n turns, obviously your solenoid can have total, suppose n turns. So then that is given as N into phi I, right? So this is how the total flux through n turns should look like. And how do you define inductance? So inductance is the proportionality constant, which relates the flux linked to your to the coil and the current that is flowing, right? So if you use this relation, you see that the inductance is given as this, right? Mu 0 n square A into L. It's basically dependent on the geometric parameters of your solenoid, right? So this is called the self-inductance of the coil. So I saw there are certain questions regarding this, so I thought it would be good to share the derivation with you. Okay. So now that we have talked about a single solenoid, what happens when you have two long coaxial solenoids, each carrying some current I, but in opposite directions, right? As shown here. So what would be the field inside the inner solenoid, in between the two, and what should be the what should be outside? Can you tell me how it should be? So what should be the field inside both the solenoids, like inside the inner solenoid? So somewhere here. Any idea? So think of what is the field for each of the solenoids and what is the direction of the fields, because now your currents are in different directions, right? It's pretty simple. So basically, one should remember that outside, so if outside both, there'll be no effect, right? Because we just saw that for an infinite solenoids, there's no field outside, right? But when it's inside, so suppose if it is inside the uh, inner solenoid, there'll be fields for the first and field for the second, and they'll be oppositely directed because the currents are flowing in opposite direction. So this is how the field should be inside the inner solenoid. But in the second region, which is between the two, obviously it's outside the inner solenoid, right? So there the field due to the inner solenoid is zero. Only this outer solenoid contributes, right? So you just have minus mu zero I into z cap, right? Okay. So this is how, for any kind of structures which involve solenoids, you can look into make use of the right hand thumb rule and see how the magnetic fields are directed, and you can try to find the fields. Okay. So now again you have this parallel plate capacitor, okay, but now that is moving with some constant speed. So it's again analogous to this sheet of current that we initially were talking about. And how should the magnetic field be between the plates and also above and below them, right? And what is the magnetic force per unit area on the upper plate? And what should be the speed of V so that the magnetic force balances the electric force? So these are the questions. So to start with, suppose like first question is, what is the magnetic field between the plates? So can you tell me how to start with the question? So initially we had tried with this question where you had a straight line and there was some charge lambda and that was moving with some velocity v. And we saw that that is just equal to a case where you have two current carrying wires, where the current on each wire is given as lambda into v, right? So similarly here, you can say that this is similar to the case where you have two sheets where the surface current density on each sheet is given as sigma into v and minus sigma into v, right? And if you do that, you already know, like initially we had solved this question, right? This part of the question. So now if you know that k is given as sigma into v for one sheet and sigma equal to k equal to minus sigma into v for the other sheet, and you can find how the B is for each of the sheets, you can see how the field will be, right, inside and outside. So if you do that, it would turn out to be something like this, right? Mu naught sigma into V, right? And that is pointing like this. So, and it in inwards, and it's between the plates. Anywhere outside, it's zero. Why? Because they cancel each other out, because the charges are of opposite sign, right? And now, if you want to find the Lorentz force, again, you can use this relation, right? K cross B into dA. and you would see that this is how the magnetic force should look like. You know the expression for the electric force, and if you try to equate them, you would again see that for them to be equal, this v should be equal to speed of light, right? Okay. So this type of questions are very essential in the sense that so it's analogous to the parallel plate capacitor problems, right? And so I think there are this kind of questions in your assignments as well, where you have some k specified on some surfaces, and you want to find how the fields should be inside or outside and in different areas. Okay. Now, if you have to compare between magnetostatics and electrostatics, this is the comparison. So it's so just like in Gauss's law, from the Gauss's law, you can see that the divergence of E is given as rho by epsilon naught, while curl of E is 0. Here you have divergence of B equal to 0 because no monopoles exist, and then curl of no magnetic monopoles exist, and curl of B is equal to mu naught J. This is from the Ampere's law. So now that we know this, you can see that because just like when we had curl of E equal to 0, you could write the electric field as minus grad V, and you could get some idea of some potential. Similarly here, because divergence of B is 0, you can have a vector potential A, where curl of A is equal to B, because uh, divergence of curl of something is 0, right? So this is how you can relate a vector potential A to the magnetic field. And if you expand it, you get something like this. Now here you have some freedom, right? You can choose your divergence of A to be 0. How? So you can add something whose divergence is 0, just like it's done here. And if you do that, you see that, so basically, initially, suppose your potential was not divergenceless, but you add some grad lambda, like some grad lambda kind of term, gradient of lambda, whose divergence, like when you do that, it becomes 0. So if you together with that extra term, you can make your A to be 0, right? And that would not change your field. So using that freedom, you can put this term to 0. So what you get is then del square A is equal to mu naught J. And that is again the Ampere's law, but now in terms of your vector potential. So from this, you can in a way define, this is how your the vector potential should look like for a current volume current density over some volume, and you're integrating over it. So this is how your um, vector potential should look like. And from here, you can actually go back to your expression for, you can go back to your expression for B by using this relation. Okay. Now, here, what we are trying to do is, now this part is very important. Okay. So this is something we already know from electrostatics. We know how the normal and the tangential components of electric fields are below and above a charge sheet. And now if you have to do the similar thing for a sheet carrying carrying a surface current, this is how it is to be done. So we know the divergence of B is 0, and that tells you that the normal components are continuous. Okay. But now here you have some discontinuity in the tangential component. It's opposite to what you got here. So here, as you can see, that the tangential components have a discontinuity, which is given as mu naught K, where K is your surface current density. And that comes directly by considering this Amperian loop. So in questions where you have to suppose there is some given charge, some charge density over some area, and you want to find how the magnetic field will be. So you can use this relation to find the fields above and below. Okay. So we'll make use of this thing in some questions. Okay. And just like we had electric dipoles, so basically what I'm doing is I'm telling you all the theories that are basically similar to, so it's similar to what we had done in electrostatics, but now we are seeing how things are extended to magnetostatics, and it's quite similar. But all of these are very important in order to understand the basics of magnetostatics and also to solve problems related to that. Okay, so this is similar to the multipole expansion that we did for electrostatics. And here what we have is a is some current carrying wire. So you consider some length element dl, okay, and what you do is you also again find the distance from the length, current element, and you find the vector potential. So that's why I introduced the concept of vector potential. So if you use the definition of vector potential, you would get some expression, okay, and from there you can again go back to the expression of field. So now if you look at individual terms, it's similar to the monopole dipole terms that we had initially seen. So here this first term is always going to zero because no magnetic monopoles exist. So there's no just single north pole or south pole. It always comes in a pair. So this term will always be zero. So it's important to look at the dipole term. And this is how the vector potential's dipole term look. Okay. And this is the dominant term. Okay. Except in the rare case where this vanishes. So now if this is a dominant term, if you do the math, this is just math. And what you see is this is how it looks like. Okay. Here, M, this is important. The magnetic dipole moment is defined as the current that is flowing in the wire into the area. Okay, the area that it encloses. Okay, so this is how you define the dipole moment for any current carrying loop. And if you do that, now you know the expression for A, you can find the dipole, the magnetic field for a dipole. And this is how it looks like, right? And the magnetic dipole moment is independent of the choice of origin. It's important to note that. Okay. And if you write it in terms of vector form, like you can also write it like this. So now that we know the expression for the dipole, the field due to a dipole moment, okay, can we find, so suppose if you have some dipole moment, magnetic dipole here, what would be the field at this point? Or what would be the field at this point, right? So this is the expression, right? Now, for A, right, what do you see? That your phi is 0, right? And theta is 90 degrees. So if you put that in this expression, you get something like this, right? Similarly, you can do something for B, right? So what would be the value of phi and theta for B? So it's very simple from this expression that in this case, phi would be 90, right? And theta is also 90. So if you do that, you get something like this. Now one can always change from theta cap or any of the unit vectors along r cap, theta cap, phi cap to the Cartesian unit vectors, right? And this is the relation that one can use. This is something we had started with. Okay. So this in a way tells you how the fields look like at different field points around a dipole, around a magnetic dipole. Now, suppose if in this case you have a dipole, you can also have a magnet, right? You can have some magnet, and then if it's a small magnet, you can think of it as a magnetic dipole. Now, in that case, if you are suppose told like some what is the field at this point, then this is the formula for that point. And then if you are asked how does it look like at this point, so you can use the similar relations, right? This is something which can be there in your assignments, where it's said that you have some magnets and there's some field at some point, and how will the field be at some later point. So if the field is specified at some point, you can use this formula to see how it looks like. So you would get the value, and then you can compare it with the field point where you are asked to find the field, right? So it's similar to what is being done here. So small magnets can be thought of as a magnetic dipole. Okay. Now talking about magnetic fields in matter. So just like we had some polarization. So if you have some system with some charges and then maybe an atom, and if you put it in an electric field, you know that it will get polarized. So similarly, there can be magnetic dipole moments that can be induced in systems. So there can be different kinds of magnetization. So there can be a diamagnetic substance where what happens is when you have an external field, the internal magnetic moments are aligned. So each of this can be considered as some current loops. And you can see that the dipole moments in this case are aligned opposite to the externally applied field. So this is for a diamagnet. For a paramagnet, what happens is initially there is no field, no net moment for the particle. But once you apply an external field, the moments get aligned to the field, right? So then there is a net moment that you can get. And for a ferromagnet, even when H is 0, so even when the applied field magnetic field is 0, there would be some net moment in the system. And if you apply an external field, the moments will align in that direction. So this is how, these are the basic, like the broadly specifying, these are the types of magnetization that can be seen in different materials. So what happens is, if you look at the field lines, this is how the field lines should look. So when the magnetic field is much, so if you have a diamagnetic material, what happens is, this is your applied field, and as you can see, the field lines move out of your diamagnetic substance. So here the densities are much reduced, and so here B is much less than H, right? While here, if you have a paramagnetic substance, as you can see, the field lines are concentrated into the system. So here B is greater than H. While in ferromagnet, it's much like there is rather more concentration of field lines into the ferromagnetic substance, and so B becomes much greater than the applied field, right? And this is how the magnetic permeability should look like in all of these three cases, right? So for ferromagnet, it should be much greater than 1. For paramagnet, it should be greater, like closely greater than 1. And for diamagnet, it's less than 1. Okay. So now that we know that there could be magnetization in a system, then we can think of the case where if you have some magnetized object, there'll be a magnetic. So if it is magnetized, so there's a net magnetization. So one can think of magnetic moment per unit volume, right? Similar to how we had thought of dipole moment per unit volume, and then we had gone to polarization. So it's similar to that. So there we already know how the vector potential looks like for a single dipole, right? And now if you have small dipoles over some area, so some dipole moment m per unit volume, okay, and over some volume it's distributed, so you can write it in terms of this integral. And if you do that, this is how your dipole, like the vector potential should look like, right? And now it's just some mathematics where you use the expressions or use the relations for divergence and gradients. And if you use those formulas, so what you get is important. You see that there are two contributions, right? One comes from volume. So that means the magnetic field due to a magnetized object can be thought of magnetic field coming from two sources. One is a volume current, which is given as curl of M, where M is your magnetization. Another is a surface current, which is given as M cross N cap. Again, M is your magnetization. So this is similar to how we had found the bound volume charge and bound surface charge, right? So similarly here, now you have bound currents. And this bound currents are actually uh, give rise to the fact that now when you use the Ampere's law, you can no longer just write it as J. So the J has two contributions, one coming from the bound currents, another coming from the free currents, the currents that you have externally provided. So if you again write the expression for the Ampere's law, now you have two contributions of volume current density, right? And you know that this bound current density is written as curl of M. Uh, uh, bound volume current density is written as curl of M. So from here, now you find this relation. So here JF is your free volume current density, right? So this term here that you get, you denote it as H, and that is called the auxiliary field, okay? So then now the Ampere's law reads curl of H is equal to JF, where JF is only the free volume current density, right? And in the integral form, it would look something like this. So if one brings the concept of susceptibility, which relates magnetization and the applied field, so in a linear system, you can say that the magnetization is proportional to the applied field, and that is the proportionality constant is given as magnetic susceptibility. And if you use that relation here, what you see is B can be written as mu into H, where mu, that is your relative permeability. So mu is the net permeability, and that is given as mu naught into 1 plus chi m, where chi m is your magnetic susceptibility. Right? So in questions, suppose that there is some material where your chi m is provided. So you can find the relative permeability of the medium. And from there, you can see how the magnetic fields and the auxiliary fields are related. So you can use these relations to find the fields and the auxiliary fields. You can also use this relation if JF is known. So if you are free, so the current that you're providing externally is known to you, you can use this relation to find H. right? And from there, you can use this relation to find B. Okay. So if you have some, long copper rod of radius R, which has uniformly distributed current, okay, so as we just saw, so here your externally applied current is specified, right? So what you do is you use flow inside, and you can also do it outside the rod. So what you see is when your S is less than R, that is somewhere inside, right? So then H into and you know what is the current enclosed. You know the total current is given as I. So current per unit area will be given as I by pi capital R square. And what is the current that is present in this region? It's given as I by pi R square into pi S square, right? So if you use that, you see that this is how your H looks like inside. And similarly, outside, you can consider the case where S is greater than R, and there the current enclosed is the total current I, right? So there directly H is given as I by 2 pi S, right? So, and if you know H, you can actually find B, which is given as mu naught H. But it's important to remember that here you can find B when you know H only when M is 0. So inside you can't find, right? You can find it only outside, because outside you know it's free space and there M is 0. So you can find the field outside, but you cannot find the field inside because you have no idea how M is inside. If you knew M, you can also use this relation to directly, if you know H, you know M, then you can find B. So inside magnetized objects, you need to know both M and B or H in order to find B. Outside, if you know H, you can actually use this relation to directly find B because there M is 0. Okay. And this comes again from, this is something we just discussed in this part, right? So this region. So now one can extrapolate this relations to the auxiliary fields, and that's what is being done here, right? So we knew this, and we can write this in terms of the auxiliary fields and the magnetization. Okay. So in questions where you have different surfaces with different surface current densities, you can use this relations to find how the field or H will be below and above the sheets. Okay. Or you can also use the expression that we just found for a single sheet and do the extend it, extrapolate those results to your question. So similar, this is something similar to what I am just saying now. So suppose if you have some region, right, and you know that the surface current density in this region is given as K1, and the surface current density in this region is given as K2, and this is how the values are. Okay, so plus 30x along this line, and this is minus 30x cap. So it's along x, right? And you know that the region inside has some, permeability, which is given as 5 into mu naught. Okay, and this is how they are placed. So it's placed, one plate is like the surface, one end of of this volume. So this surface is at z equal to 0, and this is at z equal to 3, right? So now if you want to find the auxiliary magnetic field H for z less than 0, right? So z less than 0 means below this. How do you find that? So what you can say is that for surface 1, so for the first surface, this is this surface, you know that B should be equal to mu naught K1 by 2 into y cap. How do you do that? So first the direction. So if this is the right hand thumb rule, right? So your field is directed along X. And as you can see, your fingers are pointing in this direction. So that is along y cap, right? So below it should point along y direction. And you know this from something we just derived, right? So we saw how the fields look like below and above a sheet of current, right? And it's just that same result. So that is given as mu naught K1 by 2. Now what happens for the second surface? For the second surface, again, this point is below this sheet of like below this surface, right? So if you have again this rule, you would see that, see, this is your current direction. So your magnetic field should go like this. So it should point in plus y above the sheet, and it should point in minus y. So this is how it's circling, right? So it should point in minus y in below the surface. So then it should be given as mu naught k2 by 2 into minus y cap. Obviously, it's important to note that direction, it's not dependent on the direction from the surface, right? So now what is the net B? So the net B can be given as, sum of these two B's, and here it's a minus sign because they are oppositely directed, and you can see that they cancel each other, right? So the net B outside is 0, and that tells you that H is also 0 outside, right? Now what happens in between, right? So somewhere in between, again, you do the same trick, right? So in between, what you see is for this sheet now, the first sheet, it's above the surface, right? So if you have a current flowing here, so this is how your right hand thumb rule would tell you how the direction of the field will be. So it goes like this, right? It goes in a counterclockwise fashion. And so above the plane, it should go in minus y direction. And that's what you get, right? But for the second surface, it's now still below the surface, right? So it's still in the minus y direction. So what you see is that now they add up, right? So if you add up, you can find the net B, and it's just using the value of mu naught, the permeability of free space. So if you use this value, you would get something like this, right? So this is your magnetic field value at um inside this region, right? And now what happens at a point which is above both the surface, somewhere here maybe? So there again, similar thing. Just look at the case how the magnetic fields are aligned below and above the surface, and then use this expressions, right? So now it's above both the surfaces, right? So this is how the magnetic fields look like, and then they're again oppositely directed. So they cancel each other, and you can see that H goes to 0 here, right? So what is this telling you? That now in this question, you had K1 and K2 equal, right? So they are equal and opposite to each other. And you see that the net magnetic field remains inside, okay? And outside they cancel each other and they become 0. Now, in case your K1 and K2 are not equal to each other, what would happen? You would get some net field above and below the surfaces, like below these two sheets as well, right? So in that case, this K1 and K2 would not cancel each other. That's the case. So you would get some net field here. You also get some net field here. But the process would exactly be similar to how it's being done here, right? So I saw similar kinds of question in your assignments. So I thought maybe I'll discuss this. So any question till here? Okay. So if not, any question related to anything like pertaining to magnetostatics, you can ask me. Otherwise, we'll call it a day. Okay. So if there are no questions, thank you. Okay. Thank you.